Hey everyone. First, I'd like to do a couple of things before starting. Thanks, Pablo, for the introduction. Thanks to all the supervisors, Jeff and Seb, who is up here in the front, and all the people that are helping with this project. Thanks a lot to all the sponsors, NTGS, Geoscience Australia, and Emerson Resources. And most of all, thanks for all of you to making it here at 9 a.m. to listen to a geochronological talk. You made the right choice. I really appreciate that. Okay, let's start. Penang Creek, 1933. One blind man, one partially blind man. Jack Noble, you see here, would pick up a sample from the ground, try to describe it to his friend, Weber, who is completely blind. Then, Weber would take the sample in his hand, trying to feel the texture, to understand the sample. Then, they would decide where to explore, where to prospect. And this technique worked. Together, they managed to discover gold. They even managed to discover what would become the highest grade deposit in the province, Noble Snow. And I think you all know the story. Then mining started to boom in the province. We can count over 200 mines that were present during the Tennant Creek, during the Tennant Creek golden era. But then the gold price went down. The mines started to close. But now the story is a bit different. The gold price has never been so high, and many companies are willing to invest and to explore in the province. And you've all heard about the successful stories that are happening right now in Tennant Creek. So, what is the current potential of the Tennant Creek province? And how can we explore with modern techniques what was once of the largest gold fields in Australia? To address that, welcome to Tennant Creek. Well, recent advances in technological exploration tools and new research insights can help providing insights into the geology of Tennant Creek. And we can use those tools to improve exploration. So what are those tools that we can use to improve exploration? And that is exactly the aim of my PhD here, which is to provide new tools and to provide new insights on how can we explore this province that we thought was overexplored, but actually is very, very underexplored. So there are several parts of my PhD research here. I'm not going to go through all of them during this talk, but just to give you an overview. The first one is focusing on the vectoring to ore. Basically, how can we know how close we are from an ore deposit? And this is using chloride chemistry, which is a powerful tool to vector towards our body. The second part is focusing on how can we differentiate barren from mineralized sectors. How can we differentiate barren ironstones from mineralized ironstones? And this is using hematite chemistry. That's going to come in a later stage of my project. And finally, the part that's going to be the focus of today's talk is the geochronology. How can we use geochronology as an exploration tool in Tennant Creek? And how can we provide new insights into the timing of the mineralization? So let's go into that. For people that don't know, Tennant Creek is a large province. We're talking about 20 by 40 kilometers rectangle, located in the middle of the territory. It's in a nice place, I would say. It's located 1,000 kilometers south of Darwin, 500 kilometers north of Alice Springs, and it's hosting many different deposits, mostly copper, gold, with a bit of bismuth. All those deposits are hosted within the green area you see here, which is the Warongah Formation. That's a paleoproterozoic formation made of different sedimentary sequences from Greywacke to siltstone with other formations. This formation is overlaid by the ORIGG group made of volcanics and submarine deposits as well. And then it's important to know that we have the intrusion of several magmatic bodies from felsic to mafic, such as the Devil's Tooth granite, which is here, and the Treasure Tooth monzonite, among others. As I said, many mines were exploited in the previous century in Tennant Creek. Among the famous one, we can mention Warrego, Gecko, or Noble Snow, very high-grade gold mine. All those mines are a bit different. All those deposits are a bit different. Among the main commodities, again, we can note copper, we can note gold, we can note bismuth. Some of them are exploited as byproducts, zinc, lead, selenium, or even silver. It's also interesting to note that all those deposits are a bit different in their content. Some are only gold-rich, some are gold copper-rich, some do not contain any gold, sorry. So we have a bit of diversity within the province. But overall, it's been over a year that mining has started in Tennant Creek, and we can count over 200 tons of gold that have been exploited, and much more to come in the future. In terms of geology, most of the mineralization, not all the mineralization, but most of the mineralization is hosted in what we call ironstone. Those are magnetite, hematite, chlorite, quartz lenses that are sometimes outcropping. Those lenses, sometimes those ironstones can be barren with no mineralization associated, or can be heavily mineralized. The one you're looking at here in White Devil is hosting the White Devil deposit. There's approximately 500,000 or 700,000, can't remember, sitting right below this ironstone outcrop here. Then those ironstone, when they are mineralized, they are infilled by a copper gold plus or minus bismuth stage with veining and infilling the ironstone. Those deposits have been classified as iron oxide copper gold deposits, but they are a bit different, IOCG deposits. When we talk about IOCG deposit, we can think of large systems with very wide alteration patterns, such as Olympic Dam or some deposit in the Cloncurry district. This is not something we're having here in Tennant Creek. The alteration zone is very narrow, very intense chloritization zone around the ironstone, which differs a bit from traditional IOCG system. Also, something interesting here, they are enriched in bismuth, which is not a feature we observe a lot around IOCG systems. When we look at the rocks, a few pictures, I couldn't bring rocks here, but you have some peaks here. So they are seen in the sediment of the Waranga Formation. This one is a bit chloritized. The ironstone looks like this: chlorite, quartz, magnetite, hematite. And then in the later stage, when it's infilled by the sulfides, we can get veins of chalcopyrite, bismuthenite, and sometimes native gold in the vein with many other bismuth sulfosalt mineral. Good. So now, how can we use geochronology to help exploration in the plains? To do so, let's have a look at the situation right now. On the right side of the slide here, it's a compilation of all the data that have been collected and all the ages that have been calculated prior to this study. There are two main events of mineralization occurring in the Tennant Creek province. The first one is 1860, copper gold bismuth event, measured in many different deposits. The second one, occurring 200 million years later, the one on the right side here, 1660, 1650 million years. They are separated by 200 million years. Again, that one has been measured for copper gold bismuth event, sometime in shear host mineralization, but we have also the same ironstone host mineralization showing this event here. There's actually something missing on this figure here. The largest deposit in the province, Warrego, doesn't have its age. And that could be an interesting tool because, well, that's the largest one, so that can help us provide new insights into the mineralization timing in the province. So Warrego is sitting just here, and very large system for the province. The Warrego system is made of different lodes. They are mostly zoned with, as you can see here, going from magnetite chloride, magnetite sulfide, as you see on the diagram here, copper, gold, bismuth system, very large producer over the previous century. All the stars you can see here on the right side are the samples we have been using for dating using the uranium-lead method. For the people that are not familiar with the uranium-lead method, basically it works using the decay equations of uranium and thorium isotopes into their daughter lead isotopes. And by using those decay equations with the concentration of both the parent and the daughter isotopes, we're able to retrieve an age and to calculate an age for the mineral. In this case, we're using monazite, very powerful tool for dating. Monazite is a phosphate of formula rare earth PO4, can accommodate a huge range of rare earths, plus two interesting elements for us, uranium and thorium. And when those elements are in quantities sufficient enough, we can calculate and try to do geochronology with the system. You can also note that the yttrium-rich version of the monazite is called the xenotime or xenotim, and you may see this name over the slides. They can be dated using the same method. The methodology is pretty straightforward. The only thing is when you take a sample and you want to date it, in the beginning you don't know whether there's monazite in it or not. So it's a bit of a lucky leap. You take a sample and maybe there's something you can date, maybe there's not. To do so, we're going to model mineralogy using an SEM-based technique, which means going to all the phases in the sample to try to see and separate the one with monazite from the one that have no monazites. Then, for the sample that contain monazite, we go through AMIX to locate the samples in the section. Then we go and do BAC imagery, backscattered electron, to try to understand the texture and the relationship between the monazite and our mineralization. And then we end up with a high precision LIAC-PMS dating of the phosphate. That leaves us with around 500 analyses, from which we can consider 150, 200 analyses to be good and to be usable for dating for Warrego. If we have a look at the monazite on our deposit here, what's interesting and what is great is that we have a clear relationship between the monazite that we are dating and the mineralization. They are intergrown, they are precipitating at the same time. We have inclusions of sulfides in our monazite, whether it's chalcopyrite, bismuthenite, or the weird bismuth sulfosalt, such as this one, lead, bismuth, selenium, which is a bit unnamed. And we have also clear relationship between other sulfosalts in the system. Also, we have monazite overgrowing apatite. We can have present in the sediment. Monazite is present everywhere, whether we are talking with the mineralization stage or we are talking with the surrounding sediments and the mineralized sediments. Well, now we get to calculate all our monazite. We put everything onto a diagram here. That looks a bit messy, can be hard to read. How to read that? Basically, the red line you see here is called the Concordia line. All the ellipses that are plotting on this line, for interpretation, of course, can be used for dating. Everything that's plotting on the right side, shifting to the right, these are analysis samples that have shown a presence of a lead loss event occurring between the monazite crystallization and today. And everything that's plotting to the top of the diagram are samples showing high common lead. Well, it seems a bit messy. Each of the colors corresponds to one sample. If we want like a detailed geochronology, we need to go sample by sample. No worries, I'm not going to do that today. I'm going to go straight to the result, but it should show how complex this system can be sometimes. Good, let's go to the most interesting thing. When we look at the concordant monazites, the ones that are giving robust ages, we have two clusters appearing in Warrego. The oldest one, the first one that you can see in blue here, occurs around 1925 million years. Slightly younger than the known oldest age in the province. Very clear, robust age. The second cluster, which is the most important, occurring among more than 20 samples, again, whether we are dealing with the mineralized core of the system or the surrounding mineralized sediments, appears to be at 1710. That's a new age for the province for the copper, gold, bismuth mineralization here. Again, very robust. And once again, we have clear relationship between the sulfides and the monazite. As you see here, monazite intergrowing with guanohatite, which is a bismuth selenium sulfosource. Some of the monazites here, they are a bit more tricky, I would say. They are concording onto the Concordia diagram, but you can see they are shifting a bit to the right, meaning that there may be an event of lead loss occurring between the monazite crystallization and today. We can then calculate another age, the Discordia age here, that gives us a slightly older age of 1727 with an intersection down there, an lower intercept of 600 million years. That means to us that we may be dealing with a system with a reopening around 600 million years. But basically, those ages are pretty similar. So we can think, well, we are having 1705 here, 1727, 1717, if we calculate the 76 age, which is this line here, which one can we use? Well, it's probably a bit complex. All those age may not be wrong because we are dealing with a system where there has been a bit of lead loss event. So probably it's safe to assume that we have an age between 1704 and 1727 for the main event. But for the purpose of the study, since most of the grains are concordant, we're going to use that age here for the compilation, around 1705, 1710. And finally, some of the monazites are really bad. It's impossible to do anything with those. They are undatable, basically. And this is regardless of the texture, regardless of the position of the sample. So why so? When we look at the chemistry here, all the grains that are in red here correspond to the concordant ones, the one that we can use to date and to find those two clusters. And all the yellow ones correspond to the monazite grains that we have to remove because they're not giving any age. And it turns out that all the grains that are falling on the Concordia line correspond to high uranium on top here, high uranium, high thorium grains, meaning that we need to have sufficient uranium and thorium to be ppm to date our monazite. And I'm not going to go into the details. If you're interested, feel free and come to ask me. But we came up with a threshold of all the grains with a strontium ratio under 100 ppm can be considered as monazite and giving the true age. Everything that's above can be removed as filter. I'm not going to go into detail. Feel free to come if you're interested. When we go back to our compilation, this time putting all the samples together, the two clusters are appearing clearly, the one at 1825 and the second one at 1710. And if we go back again to our first compilation we had in the beginning, our first event is occurring slightly younger than the first known event for copper, gold, bismuth in the province, although it's slightly bit younger. So maybe we're dealing with the same pulse, the same magmatic pulse that are with the same fluids within error. Maybe it's something similarly different, but we can relate this event maybe again with the first magmatic event up there. What's interesting for us is the main event we're observing in Tennant Creek in Warrego is the one at 1710. There hasn't been any copper, gold, bismuth mineralization dated at this age. The only thing that has been dated at 1710 corresponds to this tungsten molybdenum event that doesn't seem to be related with the Tennant Creek style IOCG mineralization. Interesting to note that we have the Warrego granite, which is located not far away from our Warrego system, that has also been dated at 1710. Again, maybe we could have a relationship with the intrusion of that granite here triggering the precipitation of that second stage here. No clear relationship yet, but it could be one hypothesis here. Okay, seems like dating the mineralization in Tennant Creek is a complex task with different events. How can we use that for exploration? Well, looks like Tennant Creek is a big system with fluids precipitating over a long period of 200 million years. with different pulses maybe that are coming into the province and precipitating, leaving a bit of fluids every time. We can think of a system like Olympic Dam, very big system, where over a long period of time, we keep adding fluids to the same system, increasing the ore and the size of the system. But instead of precipitating everything into one single deposit, every time the fluids will find a different trap, whether it's an ironstone or another shear zone, and precipitating a bit of this mineralization. That leaves us with something else. If the largest deposit in the province has been dated at 1710, maybe there's another deposit, large deposit like Warrego, to be found at the same age here. And maybe it could be interesting to look around the granite if this relationship is confirmed to see whether we have other systems that are in the cover at the same age. So very good. That can help readjusting the exploration models in the province. We're not dealing only with two systems, but maybe many, many more to be found in between those events. A very large system. And yeah, another challenge could be to put more constraint in the hematite crystallization, the ironstone crystallization, to tell a beautiful story about the precipitation and the genesis of the Tennant Creek fluids. That is for the geochronology. I have 4 more minutes, and I want to go into the work, the preliminary work we have done with the chloride chemistry, because it seems quite promising, and you may find that interesting as well. As you may know, chloride is a very powerful tool when it comes to vectoring. Using compositional variations in the chloride, we can be able to differentiate proximal from distal zones in many different deposit types, whether we are dealing with porphyry, with skarn, with VMSs. Can we do the same thing with Tennant Creek? No, that's the question. There are 2 approaches for this. First, work on the deposit scale, meaning to take samples and to be able to know how far we are from a mineralized system. And the second one, on a more regional scale study, to understand the variations using chloride between our copper systems, our gold systems, our barren systems, and whether when we are going to take a sample in the Tennant Creek province or beyond, to be able to know whether we are dealing with a mineralized system or a barren system. So these may have application not only for the Tennant Creek province, but for all the surrounding province and the undercover deposits. And I'm going to show you a few of the preliminary results that we had, very promising as well. We are dealing with the Juno deposit here, bismuth, copper with a bit of selenium as well, and obviously lots of gold in the Juno deposit. Taking sample starting from the mineralized part, or from the sediment part, non-mineralized, going all the way to the core into the high-grade mineralized zone. When we measure the chloride using ICP-MS and we put everything, we can see some trends. When going towards the mineralization, we do see an increasing content of cobalt, of iron, and a decreasing content, for example, of barium and vanadium. And which is interesting is that we do not have like 2 clusters, mineralized and non-mineralized, but we do have a gradual decrease, a continuous decrease when we move away. Meaning that what we are seeing here, this trend, if we see it at it's roughly 100-meter scale, how far can we see this trend? What's the extent of these fingerprints in the Tennant Creek deposit? Maybe we can follow this trend for kilometers, and in this case, that would be super helpful. And we have reasons to think that it would be possible to get this fingerprint over several kilometers. So imagine you take a sample, you don't know how far you are from a system. You measure the chloride chemistry, and that tells us if you are 2 kilometers away or 100 meters above a mineralized system. That could be very helpful in the future, not only for Tennant Creek, but for beyond. And I like to finish on some thoughts on the Tennant Creek province. And the same way this chicken is thinking about its future, that comes from the Daly Waters pub for the people that are that know this place. The same way this chicken is thinking about this future, we can think about the future of Tennant Creek as being very promising. By combining new exploration tools, new geochemical tools with the new discoveries that are being made right now, maybe we are going towards a second gold rush in the Tennant Creek province. And on this beautiful sunset over the Tennant Creek province, thank you for listening.